by the Yen-Chen from Central University. And Yen-Chen is a leading expert on the supernova observation. And Yen-Chen got a PhD from the University of Oxford in UK in 2014, and later he went to UIUC as a first postdoctor, then moved to the Santa Cruz with his boss, rightfully, and for another 2 years. Then he got a ASIAA fellow, and come to the NLJ in 2016 for another 2 years. Originally, Yen-Chen should have come to ASIAA as a second place for the ASIAA fellow. However, fortunately, and got a faculty position at the NCU. So he just lost, and we are happy for him. And Yen-Chen today, he will talk about proving the evolution of the supernova type 1A with the ejecta velocity. So let's welcome Yen-Chen.
Thank you very much for inviting me. So my talk today is about type 1 supernovae and how we could understand these type of explosions with ejecta velocities. So actually the background here is the galaxy, but today my talk is not about galaxies. Actually it's a host galaxy of type 1 supernova. I don't know if you can tell there is a supernova, type 1 supernova in this galaxy. Probably very far. Anyone want to guess?
Lower right?
Lower right. You mean like this part?
Right below the bulge.
Right below the bulge.
The
like
two, right dots.
Yeah, good guess. So yeah, there's a supernova here. This one, right one. It's called supernova 2006X. So it's a type 1A, and very special type 1 supernova because it has a very high velocity, high ejecta velocity. So that's one of my focus today. Try to understand these kind of explosions based on their velocities. So in case because not all of you here are experts in type 1A, also supernova, even supernova. So I'll try to do some brief introductions, like what is type 1 supernova. So of course, type 1 supernova is just one kind of many supernovae, many types of supernovae, and it is bright, very bright, sometimes comparable compared to a host galaxy, and they are associated with the death of stars. So actually, for all the supernovae, we, no matter its type, they are all related to the death of stars. So we'll discuss this later. And this is just a demonstration or example of a type 1 supernova explosion. It's called supernova 1998 BU, exploded in M96. So you see here, we indicate by this arrow is the location of the supernova. And we made an animation here based on its light curve. You see that here we have two light curves. One is blue, which is taken with bluer filters, and the redder one is probably longer filters. So you can see that for type 1 supernovae, such kind of explosion takes about 2 weeks to reach the peak velocity, and then a couple of months to fade away. So of course, not all the type of supernovae have such a light curve, similar light curve. For example, for some type 2 supernovae, cold type supernovae, they could have pretty flat light curves. So it depends on the type. So
why do the light curves differ in shape?
So that's a good question, please. So the blue one usually means bluer wavelengths, like B band, and the redder light curves are usually longer wavelengths. And we found, for the radio wavelengths like I band and Z band, they often show this second peak. We think it's due to recombination photons at later times. Some iron group, they emit photons and recombines at later times, and it will be at longer wavelength, like near infrared. But it's due to the recombination. When supernovae cools down.
But don't you have spectra to show anything?
Yes. There's
So all continue?
well, I mean, at later times it should be in nebula phase. There should also be emission lines.
Mm-hmm.
Yeah, there are also emission. Actually, at this phase, which is about 3 months maybe
Yeah.
after the peak, the spectrum is dominated by emission lines, not pure.
In the red. How about in blue?
In the red and both optical and near infrared. But mostly the red wavelengths.
Okay,
Not
so
the blue one.
most emission lines are in the red one?
Yes.
Okay.
Yes. So that's why you can see some, at the second peak. But
So it's not really a supernova itself, it's already in the nebular phase.
yes, it's nebula phase.
So it's not a supernova like,
It's not
it's getting to the environment.
well.
It can be
No,
environment kind of things.
It's
maybe the blue one is think about if the optical light curve is already quite faint. And I think those rebrightening and the long wavelength is due to the recombination of the iron to
Iron, yes, those iron lines, those
Yeah.
when supernova cools down, then those hot materials, the elements, they cools down, then emit photons.
like a recombination of the hydrogen.
Like in
Yeah.
Java?
Yeah.
Yes, something like that.
Yeah.
Yes.
Oh, my line.
You're right.
Java.
Yeah, okay, thank you for the question. So, traditionally, type 1 is just, like I just said, it's just one kind of many types of supernovae. And there are at least like more than 10 major types of supernovae. And if we want to include some subtypes, those very rare and minor types, it must be like 1 to 30 types. So conventionally, we classify the type 1, we classify the supernovae based on, observational properties like spectrum and light curves, but mostly spectrum. So for example, we can separate the supernovae into type 1, right, and type 2 based on whether there's hydrogen, broad hydrogen associated with the supernova, not the host galaxy. There's hydrogen in the spectrum, right? If there is hydrogen, plenty of hydrogen, then they will be classified as type 2. And if there's no hydrogen or negligible hydrogen, they will be classified as type 1 supernovae. And you can see that for type 2, there are, furthermore subtypes like 1B, 2B, 2L, 2N, 2P, so many subtypes. But for type 1, you can further classify the type 1 supernovae into type 1A and, for example, 1B and 1C, based on whether there's significant silicon in the spectrum. So you can see that this classification scheme is mainly based on observational properties. It's not necessarily mean explosion mechanisms, right? For example, all the type 2 supernovae, we think they are caused by the core collapse, right, of massive stars. But for all the type 1 supernovae, they are not all thermonuclear supernovae like type 1A. There could also be core collapse mechanisms like type 1B and 1C. So I just want to emphasize that, the types here doesn't mean, it must be related to the different types doesn't really mean they have different mechanisms, explosion mechanisms. It's just a convenient way we use to separate, classify the supernovae. So for type 1 supernovae, of course, they are, the most important implication is the cosmology, right? I think that's, very well known. Sorry.
Yes, sorry. Could you go back to the previous?
Yes.
I always have a question is about the classification between the 1A and the 1B in terms of silicon abundance.
Well, not just silicon. There are many considerations. Yes, but just major. This is just very simple schematic.
Yeah, because for example, you said the type 1B, then we will think it will be a core collapse because lack of the silicon. But based on my understanding, you know the supernova explosion is at the end. The iron core collapse, then there's a silicon and other elements outside. So I don't quite understand why silicon will be less abundant in this case.
So that's also, kind of challenging for simulations. Type 1A, why they can produce so many intermediate mass elements like silicon, calcium. So there's some theory like delayed detonation, delayed DDT scenario, which expand the type 1 supernovae into lower density, which can help produce such a large amount of intermediate mass elements. But that's still a field to be explored. Yeah. But I'm not expert here. Okay, so the most important implication of type 1 supernovae, of course, is cosmology, right? Because we think they are relatively uniform. They have relatively uniform luminosities. They can be used as standardized candles to measure distance and probe the expansion of the universe. So one, a popular way we use type 1A to measure this cosmology is to use this Hubble diagram. So just to show you that this Hubble diagram, it's simple. It's just the luminosity of type 1 supernovae after some standardization process, which I'm not going to talk in details here in this talk. So basically, it's the corrected luminosity of type 1 supernovae as a function of redshift. So idea here is simple, just by comparing, because you assume that type 1 supernovae, they have pretty much the same luminosity, just based on assumption. And if you compare the supernovae, local supernovae, to those distant supernovae, you can tell what the universe has been experienced, how fast it's expanding by comparing the data to the cosmological model. So here you can see different colors here means just the type 1 supernovae discovered by different surveys. You see from rosy or low redshift surveys, some intermediate redshift, SDSS, and supernova latency survey, and the most distant one, the Hubble Space Telescope. You can see we probe the universe up to about redshift 1. That's kind of the limit based on the current instrument. So here you can just compare the luminosity of this type 1 supernovae to the cosmological model, which is represented by this black curve here. Because you assume that the type 1 supernovae, they have uniform luminosity, so your model should be able to predict at this distance what the apparent magnitude should be, and compare to your data. That should give you something like the best fit model. So that's the idea. So I think the more important thing in this diagram is probably the bottom panel here, which is called Hubble residuals, which is the difference between, the data and the cosmological best fit model, something we call the residuals. And I mention this because so cosmology, they like to use this residual, this parameter to probe, to investigate whether we can improve the schedule of this Hubble diagram. For example, if you find this Hubble residual is related to some additional parameters, then there's some trend between the Hubble residual and some parameters. That means that parameter can be used to improve the schedule of this diagram. That's what cosmologists like to do with the Hubble diagram. So we will come back to this Hubble residuals, I think, in the end of the talk when we talk about cosmology. So, although they have been used, widely, very popular, as standardized candles to prove the expansion of the universe, actually we have pretty limited knowledge, right, about this kind of explosions. So this is pretty ironic, but at least so far, based on some very deep nearby events, we put some limit. And we think type-1 supernovae, they are associated with explosions of compact objects. So it could be, I think that the best constraints is comparable to the size of the Earth, even smaller. So it could be either a white dwarf or a neutron star, right? So many people like to ask why it cannot be neutron stars. So it's based on several evidence. So for example, based on the spectra, for the figure at the lower left here, you can see that this is a typical type 1a supernova spectrum at very early times. The phase here is minus 16.1 day. So it's basically just right after the explosion. So you can see that based on this spectrum, we have some unburnt carbon and oxygen in the spectrum, which is indicated by this shaded region. So that means there are some unburnt carbon and oxygen which you won't expect from a neutron star, right? For a white dwarf, typical normal white dwarf is made of mainly carbon and oxygen. That's something we expect if there is unburnt material from carbon and oxygen. Also, from post-galaxy studies, we found type-1 supernovae can be found in almost all types of galaxies. But the neutron star is kind of left over, something left behind after massive star explosions, which should be associated with younger populations. So we think, based on many evidence, that we think type-1 supernovae, they are associated with compact objects and more likely a white dwarf. So the problem here is how to make a white dwarf to explode, right? That's the critical question to ask. Because white dwarf is something like, death of star. If nothing happens, it will just stay there and fade away. So there must be a way to ignite this white dwarf again and produce this energetic explosion. So theoretically, if a white dwarf, if the mass of the white dwarf can be, if you make it approach this Chandrasekhar limit, like 1.4 solar mass, it can possibly trigger detonation in the center, right? And explode, produce a very large explosion. But that's also not easy, because on average, a white dwarf, based on some surveys, white dwarf has an average mass of only 0.6 solar mass. So this figure on the lower left, lower right here, you can see that this is, I think, remember from survey, SDS's survey, which they observe a large sample of white dwarfs, and this is the mass distribution of these white dwarfs. So you can see that based on this distribution, the peak of the distribution is around 0.6, around 0.5, 0.6 solar mass. So that means the majority of the white dwarfs, they have a mass way below Chandrasekhar limit. So you need to find a way to increase the mass of the white dwarf and make it to ignite the central detonation. So that's the most important thing. So since then, there are many scenarios. I think many of you have seen this many times. How can we increase the mass of the white dwarf? I think here are two most popular scenarios, like single degenerate, which is white dwarf plus normal star, and it could be two white dwarfs, right? Merger event. So it's still debate. We don't have the answer at the moment. That's probably a mystery still for now. And it must be like the database, we still have no idea. Because there's no single scenario to explain all the observed properties of type-1 supernova. However, I'm not going to solve this mystery today. Yeah, single degenerate or double degenerate doesn't really matter in this study, because what we are concerned more is about their usage in cosmology. So for cosmologists, actually they care more about whether it's a Chandrasekhar chandrasekhar, near chandrasekhar vital explosion or not, right? Because they are used as standard candles. They should, we expect them to have uniform luminosities. So, cosmologists, of course, they hope that all of the type 1 supernovae, they are near chandrasekhar mass explosion, because that means every time it explodes, the white dwarf has similar mass. It should have similar explosion energy, and it should produce similar luminosities. That's why they can be used as standard candles. So that, I think the question I would like to address in this talk is whether all the type 1 supernovae are associated with chandrasekhar mass white dwarf explosions or not, or there are some combinations. So here just some demonstration of chandrasekhar mass white dwarf explosions. Just wrote this by myself. Assuming there's a carbon oxygen white dwarf, and conventionally, if you have a layer, create hydrogen, a layer of hydrogen, or if it's a merger, if you see carbon oxygen layer on a donor star, I don't care where it's a white dwarf, another white dwarf or a normal star. I don't really care. I'm just wondering whether you can ignite white dwarf near the chandrasekhar mass or not. Right? So traditionally, you have a layer of hydrogen or carbon oxygen, and until you reach some critical mass, you can trigger detonation in the center, right? And explode the white dwarf. So that's the best situation. But this kind of scenario has some, it's not consistent with some observational properties such as the ejecta velocity. So that's what I'm going to focus today. So before that, I just want to introduce what is ejecta velocity mean here. So ejecta velocity, what it measures how fast the materials of a supernova expand, right? It's being ejected by the explosion. So typically, we measure the ejecta velocity based on the spectrum, usually the near peak spectrum. So this is again the typical type 1 supernova spectrum near mass. And there are many lines we can measure. Usually, people in this field, we measure silicon line because it's relatively pure and simple. It's not contaminated by other lines. So we measure the line velocity of silicon at this 6150 meter here, which is also one of the most important characteristics of the type 1 supernova. So we measure this line, measure the line velocity, and that's what we call the ejecta velocity of type 1 supernova in this study. Okay, any questions so far? So
But it's absorption line, right?
it's absorption line. We measure the minimum of the absorption.
So it should be blue shifted.
Yes, it's always blue shifted. Yes. So it's a blue shifted line. So, like I just said, that near Chandra explosion is difficult to explain the distribution of ejecta velocity. So, for example, this is the distribution of silicon velocity, right? Just a histogram of a large sample from a low redshift survey. And we found it's not a Gaussian. This distribution, I know it's pretty complicated here, but if you just focus on the histogram, it's the raw data, the observational data. It's like there's a tail, right? It's not just a single Gaussian symmetric distribution. There's a tail towards high velocity. So for near Chandra, white dwarf explosion, or if you want to calculate the ejecta velocity of a supernova, it's pretty simple because you know the total thermonuclear energy, right? And the kinetic energy is just the difference between the total thermonuclear energy. If you subtract that energy from, if you subtract the binding energy of the white dwarf from the total energy from this thermonuclear gradient, you can get the kinetic energy and calculate the ejecta velocity. And we found for the near Chandra mass, because the white dwarf is always near Chandrasekhar limit, which has a pretty narrow range of velocity. It always explodes at similar mass, right? Similar binding energy. And it's hard, it's difficult to explain such a wide range of silicon velocity, especially if there's a tail towards the high velocity. So there's this study trying to fit this distribution with the bimodal distribution, which is represented by this blue one, the blue curve and the red curve here. They think there could be this distribution can be explained by two populations. One is here, has extended to a higher velocity, and the other one here near 11,000 kilometers per second and has a relatively narrow dispersion. And you cannot, if you try to fit a unimodel, it's like the dotted line here. It doesn't fit very well. So they think, based on this diagram, there is possibility that type 1 supernovae, they may not be simply just produced by a near tangential second mass explosions. There must be something more interesting or some additional component, additional population. So after that, there are many studies trying to figure out, trying to study whether the supernovae, type 1 supernovae, with higher ejecta velocity are very different from those have normal, relatively lower velocity. We call it normal velocity, but just lower velocity group here. So conventionally, we use this 12,000 to separate the two groups. Of course, it's not perfect. You can see that there's an overlap between the higher velocity group and the normal velocity group over here. But just hope that the contamination is probably not large, and if we have large sample, we can probably tell the difference. So this is what we are going to focus in the first half of my talk. Try to figure out if there's any difference between high velocity type supernovae and normal velocity supernovae, or they are just produced. They can be produced by a single population or not. So first figure here, this figure shows you this is absolute magnitude before, without any dust correction, dust extinction correction. I know it's a bit complicated, but just, it's before any dust extinction correction, the velocity of type 1 supernovae as a function of the color axis, EB minus V. So here the data, so they're trying to separate supernovae data based on their silicon velocity. Like the blue ones, the normal velocity type 1 supernovae, the red ones, high velocity type 1 supernovae. And the slope here actually represents this RV. Because this absolute magnitude is without dust extinction. If you plot against the color axis, that means this slope actually means the extinction ratio. So you can see that they try to fit a linear relation to this two groups separately, and they found they have very different RV. That makes
Yeah, can I ask how did they estimate the extinction?
The extinction, I mean this,
Right.
there are many ways. Like, for example, from the supernova spectrum itself, you can measure the sodium lines. The sodium lines, like the equivalent weight of sodium lines. And if you have larger equivalent weight, that means you probably have more dust extinction. And also, I forgot how they do that in this paper. Yeah, but
Isn't that the host galaxy? That's at HOST, right?
Yeah, that's the host galaxy. So
So
basically,
it's
the
in
host
the
galaxy,
host
you can use Balmer decrement or
Yeah.
something like that. I hope they use that. I don't know. Yeah. So if this is host galaxy, just maybe they take a host spectrum near the supernova location and try to determine the reddening or dust extinction based on the spectrum at that position. That's, I think, the most precise way to measure the host extinction. So basically, they tend to have two different RVs. Because RV, I'm not sure if you know what RV means. It's related to its dust properties. Right? For example, our Milky Way here, RV equals to 3.1, or maybe the typical value of 3.1. And for high velocity and normal velocity supernovae, they tend to be lower, especially for high velocity type 1 supernovae, it's about 1.5, where the normal velocity is about 2.3. So they have a very different, maybe that implies they have different dust properties. So this cumulative distribution function here, I think they showed the B minus V, which is the color of the supernova, type 1 supernova. It's not the same sample as the previous one, it's different paper. So what they measure is the color of the supernovae. So for type 1 supernovae, we usually use B minus V at peak luminosity as the color. As their color, and the normal velocity ones is shown in blue, this blue curve over here, and the high velocity one is represented by this red dotted curve. Okay, there are two red lines I know, but this dashed line here, dash curve, is just a shift because they found, on average, a high velocity supernovae they tend to be redder than the normal velocity type 1 supernova. And if you shift like 0.1 magnitude, you can get exactly the distribution, the same distribution. So they found that for high velocity type 1 supernovae, they tend to be intrinsically, maybe not intrinsically, tend to be redder than the normal velocity type 1 supernova. So this figure shows you the polarization. So because measuring the polarization in for supernovae is critical because it tells you whether your explosion is symmetric or not, right? It's related to the geometry. So this figure shows you this polarization of the silicon line against the silicon velocity. So you can see that if you exclude these two outliers here, in their fitting, they exclude these two data points. And there's a linear relation, pretty significant linear relation trend here, where they found the higher velocity type 1 supernovae, they tend to have higher degrees of polarization, which means their explosion could be more asymmetric than normal velocity type 1 supernova. Of course, they don't have many large sample over here, but that's a clue, hint that there could be such a relation, which means their explosion could be very different in terms of the symmetry, in terms of geometry. So another evidence here is from their host galaxies. So they could be very different from, because host environment is a good way to check whether they could have a similar mechanism related to similar populations underneath. So here, this is a Nature paper actually in 2013. So here, it's the silicon velocity as a function of the distance of the supernova to the center of the galaxy, as normalized by the size of the galaxy. So basically, it's probe a location for the supernova, whether it's further away from the galaxy or not. So again, the red colors here represent the high velocity type 1 supernova, where blue colors here is normal velocity type 1 supernovae, and they found there is a significant difference in terms of their distribution, their location in the galaxy. So this is a very nearby sample, so that's why they need to do this kind of study. Or you need to be able to resolve the location of the supernova. So they found the high velocity type of supernovae, they tend to be found, they tend to be locate near the center compared to the normal velocity type 1 supernovae, which can be found both the outer part, also the inner part of the galaxy. So they interpret this as a metallicity effect because there's a metallicity where the galaxy, where the inner part of the galaxy should be more metal rich than outer parts of the galaxy. And of course, these high velocity supernovae, since they are more than apart, so they that means they are not related to those halo stars, which tend to be meta poor and old populations. Yeah, so this is they have both spirals and ellipticals. I don't know how they can tell with ellipticals. There's some concern about this because elliptic galaxies are quite dispersed. I don't know if the location means anything. But if you don't look at, just ignore these elliptical galaxies, just look at the spiral galaxy, which is these solid symbols here. You see such a trend. So it seems like metallicity could be important source in producing this, high velocity components supernovae. So this is further supported by my study 2 years ago, which is just, at the major stellar mass of the host galaxies, and try to compare them with the silicon velocity. So you can see here again, it's the silicon velocity as a function of the host galaxy stellar mass, the total mass. And again, I think the color coding is the same as the previous figure. The high velocity ones, they are red ones, and the blue ones are normal velocity supernovae. And I found that for this high velocity supernovae, type-1 supernovae, they tend to be found in massive galaxies. You see here, most of them have stellar mass above 10 to the 10 solar mass. Where for normal velocity type-1 supernovae, they seems like they can be both low mass and massive galaxies. The lower panel here is just the cumulative distribution of these two populations. So I think this is kind of consistent with the location study, right? Because metallicity, the more massive galaxies, they, we think based on the mass and metallicity relation, they should be more metal rich. But of course, we don't really consider star formation here, because more massive galaxies for those galaxies in that sequence, more mass means they also have more star formation. But we found we checked the global star formation rate with our sample, but we don't see any significant difference between the normal and high velocity supernovae. So this is further supported by the morphology, where this is a collection of host galaxies, high velocity type-1 supernovae. So we found that based on morphology, they can be both late type and early type galaxies. It's like half and half. Okay, you can see spirals and some elliptical galaxies. So it looks like there is no preference on the type in terms of morphology of the galaxy, which means the star formation or the age might not be a dominant effect. So metallicity, seems like metallicity is a reasonable guess here. Okay, any questions?
But from these figures, I don't see those high velocity supernovae are close to the central region of the galaxies. Is that correct?
Yes. So here is just a small sample. It's a different sample from the other study, but looks like it's not close. But in terms of the galaxy, the size of the galaxy might, when you do a statistical study on a large sample, it might be close to the center of the galaxy. Well, of course, you can see, right, compared to the size of the galaxy, you can see it's 1.7. It's like a limit for spirals. But just by visual inspection, it's not very close. But in terms of the size of the galaxy, they could be some significant difference.
You only plot those triangles of
Oh,
large.
triangles are just location. Yeah, the triangles are location of the supernova.
So are these for the high velocity or normal velocity?
They are all high velocity. All high velocity.
But Yen-Chen, correct me if I'm wrong. Well, in the local universe, massive galaxies tend to be elliptical.
proportionately more spirals than ellipticals.
Yes, actually, it's not half and half, but about 6 to 4, something like that. I mean, I just show just a very subsample. Subsample. I didn't really count in total sample how many, like exact fraction, but I think it's about 6 to 4. Every 10, if there are 10 galaxies, probably 6 are.
I guess the question is compared to the field, whether you preferentially select the type.
Okay. Yeah, I didn't.
That would be the question.
Okay, I didn't do that such a test. Yeah. I'd be interested. Yeah, because based on this study, they claim, not just methodicity, the high velocity supernovae, they should also be younger because they trace the light. I didn't show that plot, but one of their conclusions that they are not just meta-rich but also younger. But I don't know if that's, I don't really agree with their conclusion because we did some very rough analysis on soft emission rate, both local and global. We didn't see a significant difference between high velocity and normal velocity supernovae. Any other questions? So that's just at least several difference, significant difference between high velocity and normal velocity type-1 supernovae. And I think the most important question is to ask whether what's their origin, whether they are different from normal velocity type-1 supernovae. So I said the origin of high velocity supernovae and possibly part of the normal velocity supernovae because when you check this distribution, if you regard this red curve as a distinct population from the blue curve, and there is some overlap over here. And this population contains both high velocity and normal velocity type-1 supernovae. They could share the same origin, but just in some just in some mechanism they can have both. This kind of mechanism can produce both normal velocity and high velocity type-1 supernovae. So no matter which scenario, should try it need to meet all the requirements here. Like for example, to produce high ejecta velocity, which is hard to be produced by near center, right? And maybe based on that distribution, we can also produce low velocity. But based on that distribution, it doesn't really mean it's physically distinct. It just happen to can be better fit by a double Gaussian. So you have question.
Yeah. So Yen-Chen, I don't think the methodicity is a good correlation here. That's because when we look for metal pool stars, we also look for some of the halo stars. So the star methodicity can be quite low. Even the gas methodicity can be high around the center. So the gas methodicity and stellar methodicity may not necessarily correlate in that case. So my personal interpretation is the stellar population. So inside the halos, you can have really all stars and the binary stars. There will be sufficient time for them to evolve into two white dwarfs and due to gravitational wave, the white dwarf then collapse into the subchannel signal model. That takes a lot of time. So they have the older populations, like the galactic halos. So this population not methodicity.
You mean population? You mean?
I mean that you form those stars very old, and those old stars they will go into around the halos. They will sit around the halos. And young star will be on the spirals.
But what about high velocity?
The high velocity was due to this one-day explosion is by the subchandrasekhar models due to the two white dwarf merge. And those time actually really long. I mean, if you using the gravitational wave to dissipate the orbit of the two white dwarf, that takes a long time. So it takes time. So need to be old enough. So need to can be thick at the halo center.
So you think it's the age?
And then they will produce high velocity ejecta and also asymmetry structures.
Yeah, still, I think it's still debate. I'm still, trying to think whether it's could be metallicity or age.
Yeah, but how metallicity affect the ejecta velocity?
Yeah, so that's what I'm going to ask. In the end of the talk, maybe these kind of scenarios require, because metallicity affect like the mass of the white dwarf, also the accretion of the white dwarf, in many ways. Maybe it's such a mechanism. Just need to be.
Yeah, we are the stellar evolution. We are supernova folks. So the metallicity affect the stellar evolution. The supernova is one of the most important ways through its mass loss. And that will determine at the end how much mass you get, so what kind of supernova you can grow up or not grow up for white dwarf mass. That's only the major difference in terms of metallicity effect.
Okay, let's finish the talk and we can.
Yeah.
So here are all the requirements. We need to explain the origin of high velocity supernovae, like whether they can produce high ejecta velocity and both low velocity, low ejecta velocities, and they tend to be much rarer, and different dust properties. Explosions based on polarization tend to be more asymmetric. And high velocity still in question mark. We don't know whether it's a very significant requirement or not. So, so recently theorists been trying to figure out whether there is a scenario which can explain all of this, or most of these criteria. So one of the most promising scenarios is called subchandra. In contrast to near chandra, subchandra second mass explosion means the white dwarf can be ignited way below the chandra second mass. Okay, even when still like 0.6 solar mass or 0.7 solar mass, you can still ignite this kind of white dwarf and explode as a normal type 1 supernova. So in this scenario, what they really need is a different shell, a shell with different elements. Like, for example, here's another white dwarf. So you are accreting helium. If you have enough helium, not just hydrogen or carbon dioxide, if you're accreting helium there from whatever donor star, if you have enough helium, it's possible that you can produce a type 1 supernova. Even the mass of the white dwarf is way below 10% mass. So how? So if you have enough helium here, it's possible to produce a helium flash near the surface of the white dwarf, boundary between the layer and the surface of the white dwarf. This helium flash is similar to the helium flash. Students should know that there's a helium flash. At the end, at the last stage of the red giant, when it's entered into the horizontal range. When helium burning produces, at a degenerate state, it could be very explosive and produce a helium detonation. So if you are accreting a helium, you can produce a energetic helium flash. And this kind of flash can drive some shock waves into the center of the white dwarf, which squeeze the center and raise the temperature of the core, produce another detonation. It's called double detonation. So this kind of double detonation, again, can also produce explosion. Type 1 supernova. So let me go back to this. So let's see if this kind of scenario could meet all the requirements. First of all, okay, produce high velocity or some normal velocity ejecta. So assuming observer is here, your line of sight, the helium detonation here should be able to produce some, some heavy elements like radioactive materials, right? Like silicon, calcium, iron, or something here, because it's near the boundary, near the surface, outer layer of the supernova. They should be very high velocity. Because based on the normal, if it's a normal near-Chen explosion, when the material or element is near the center of the galaxy, you should have lower velocity. Right? But if it's closer to an outer target, you should produce high velocity ejecta. So this is kind of based on your line of sight and viewing angle. If you're looking, just right at the line of sight of this first detonation, it's high velocity. If you are, you're seeing this light at the opposite direction or other direction, if you produce normal velocities for it.
Yeah. Inside, based on my understanding, probably this physical picture is not totally correct, but it is partially correct. The thing is, helium detonation, you create a shock wave, but actually that shock wave, in principle, won't be able to just blow up the star. Otherwise, helium flash will just blow up all the stars going to AGB. Does that make sense?
You mean blow?
I mean,
blow up. Okay.
Blow up. So, as I know, based on Chicago group, is the helium flash will produce shock wave, and that shock wave will run around the star. So shock wave eventually will be converging at the center.
Yeah, that's the details. I'm not the theorist.
Yeah.
So based on simulation, you're probably right. But just, whatever, they will eventually converge here and produce the carbon detonation.
So that actually is many shock wave like put in the center among the explosion.
Okay, thanks for the explanation. So I think this kind of first detonation here depends on your viewing angle. You can see either the high velocity or normal velocity, or lower velocity ejecta. And regarding the dust property, or whether it can produce red and supernovae, if you are seeing the supernovae, the line of sight of this first detonation, the materials produced by the ashes of this helium detonation can produce serious line blanketing effect, which will make things redder, and will probably make very different dust properties along the line of sight. And if you are looking at this supernova at a different viewing angle, you'll probably see a very different color. So this high velocity is related to the dust over here produced by the first detonation. And in terms of geometry, for near-Chen, it's exploded from the center of the galaxy, right? Ideally, so it produces relatively uniform explosion, which has zero polarization. But if you already ignite the supernova, the wido, right, the one side of the wido, and then have such a top detonation, it's expected that it's highly asymmetric, because you are not igniting the wido, right in the center of the wido. So distribution of the material here is not symmetric. So last thing, metallicity, I don't know. That's what I'm trying to ask, whether or not it's age or metallicity. If it's metallicity, why metallicity have such an effect in this kind of channel? Is it related to a donor star? It would be with the helium from a donor star, whether it's a helium white dwarf or a helium star, probably not helium star. I think so far people think it should be a helium white dwarf, more likely. The how metallicity or age is related, perhaps no solid, very firm answer at the moment. Hope theories can help a bit on this issue. probably skip this. So back to cosmology. That's what we. For cosmologists, they care more about whether they could be uniform explosions. So it's natural to expect that this kind of velocity could evolve with the redshift, given their preference for the host environment, right? Because high velocity type-1 supernovae, they prefer massive galaxies. I think that's significant. So when time passes by, if you plot the stellar mass, so this figure shows you the host galaxy stellar mass as a function of the redshift. These are all from type-1 supernova host galaxies. We found at high redshift, the stellar mass tend to be tend to have low stellar mass of galaxies. So you see that made of different surveys. Green symbols here just average. The bottom panel here is just a fraction of the galaxies which has stellar mass larger than 10 to the 10 solar mass. So it's decreasing. So if the high velocity type-1 supernovae can only be found, or mostly found in galaxies more than 10 to the 10 solar mass, we should expect there should be an evolution, right? It should be rare high velocity supernovae for high ratio. That might have some impact on cosmology. So this is the first attempt. My paper 2 years ago, we used a low Z sample. So it's just a low redshift sample. We drove the redshift out to 0.2. The silicon velocity is a function of redshift. And I don't really trust this result because it's just the redshift up to 0.2. And it's pretty close to the limit of the survey. So it's probably not real. So, but still, I found there might be some hint that this high velocity is more than 12,000 kilometers per second supernovae. The fraction tend to decrease with the redshift. It's consistent with our prediction from host galaxies. So just recently, in preparing another paper, we have a larger sample with different surveys from different from different surveys like very nearby ones and PDF. PDF is the one I showed in this video. Those are the blue one from ratio 0 to 0.2 here. And add more sample here in the high ratio surveys. So you can see that it's significant that the high velocity type-1 supernovae, they tend to be rare. There's a distinct difference in terms of their redshift distribution. Where high velocity type-1 supernovae, they tend to be found in the local universe, more local universe, compared to those normal velocity type-1 supernovae. Here is the CDF accumulative distribution. So it's significant. My case test is like below 0.0000 something. So I think this is another evidence supporting that. Supporting that they could be very different. Like the high velocity supernovae, they prefer host environment and local universe, where their counterparts, it doesn't really matter. So this is just another plot showing that just the cumulative distribution in terms of the redshift. The low Z and high Z. This Z means redshift. Okay, the low Z and high Z data they tend to be offset in the velocity, silicon velocity. Where the high redshift tend to be lower silicon velocity. Okay, so is that really an evolution? Because when we talk about evolution, we mean a single population with similar object, which their property evolved with redshift, right? But it's not the only explanation. If there are more than one population, there are two populations. Their change in fractions would also produce such an effect, right? if the high velocity supernovae and normal velocity supernovae, they are really two different populations. Their change in fractions could also mimic such an evolution effect. So here, I investigate this by plotting again the distribution of silicon velocity, and I separate into low Z sample and high Z sample. So you can see that for low Z sample, it's similar to what I've shown in the beginning of the talk, right? There's a tail, and it's better fit by model distribution. But for the high Z sample, maybe it's smaller sample size, but at least based on what we have at the moment, it can only be fit by unimodel. If you try to do a bimodal fit, it's not going to give you any reasonable solution. So you can see the tail also, for low Z, can be extended to like 16, larger than 15 kilometers per second. But at high redshift, it's kind of, such a tail is not significant. So maybe there's also possibility of just change in supernovae demographics, because at high redshift, high velocity supernovae, they are rare. So you can see such an evolution, but it's not really an evolution if you're talking about two populations. So impact on cosmology. So this is the last slide. So as I mentioned at the beginning, cosmology like to use Hubble residuals to see if this parameter could have impact on cosmology, can be used to improve the cosmology. So here we did the same thing. We plot the Hubble residual as a function of the silicon velocity to see if there is any trend. So we found there are some trends that for high velocity supernovae, which is about 12,000 kilometers per second here, they tend to have more negative Hubble residuals. Just compared to cosmology models, they tend to be negative, okay? Because it's a subtraction between model and data. More negative Hubble residuals. Of course, data here is not very much, still a small sample size. And for normal velocity high supernovae, they tend to be positive Hubble residuals. So in the future, if we can separate the two populations, not just based on silicon velocity, because if you just based on velocity, it's not going to give you clean separation, but there's an overlap, right? If you can use some other parameters like stellar mass or other parameters, maybe we can separate the population. That can probably give you more significant trend on Hubble residuals. So that means, if there's a trend, maybe we can use silicon as additional parameter to standardize the type 1 supernova, to standardize the luminosities of type 1 supernova, and reduce the scattering of Hubble diagram. So I'm going to skip this figure. That's just the Hubble residual as a function of stellar mass. The reason I mentioned this, I'm trying to show this figure, is that they found, the supernovae in more massive galaxies, they tend to be more scattered, much scattered in Hubble residuals than low mass galaxies. I guess one of the reasons probably in massive galaxies there could be a mixture or more contribution from, for example, subchamber explosions. But for low mass galaxies, maybe it's more the population is dominated by the Yen-Chen Pan. Just my guess. So that's why we have a different dispersion over here in terms of the stellar mass. Okay, here's the summary. I'll just leave it here because I'm a bit over time. Yeah. Thank you.
Thank you very much. Any question for Yen-Chen?
Thank you for your talk. So I have two questions. The first one is, I'm just wondering whether or not the ejecta velocity changes as a function of time during the explosion or during the light period of this.
Yes. So, so the ejecta velocity we measure here is near peak, at the peak luminosity.
At the peak luminosity.
So, of course, it evolves with time, right? From at the beginning, it should be very high velocity, and then gradually decrease as some, and be slower and slower. But if you just pick one epoch, usually peak velocity, and compare the luminosity, compare the velocity at the same epoch. That should be fine.
Okay.
Yeah.
Okay, thank you. And another question is about the redshift evolution you mentioned. I'm just curious about because you mentioned that for those high velocity type 1 supernova, they tend to have more dust, right? And if someone is trying to detect those
Yes.
type 1 supernova at higher redshift, then if it's a magnetic limit survey, then the dust extinction might obscure the detection of those sources.
That's a good question. You're correct. You're asking whether there's a Melquist bias or not. Whether this high velocity supernovae, they could be intrinsically fainter than normal velocity, then could also produce such a trend. So in terms of the peak luminosity, we found high velocity supernovae, they are comparable to normal velocity. They are redder, but they have lower RV. So that means their extinction is not that high, compared to the normal velocity supernovae. So actually we found the luminosity in terms of optical in D band or R band, they are similar. There's no significant difference. So that means this evolution should be caused by such an effect. Okay.
Thanks.
One quick question. Yen-Chen.
I think it's very quick. Does the magnetic field of the white dwarf have any effect on explosion? Or is
You
it
mean what
negligible?
affect explosion?
Magnetic field.
Magnetic field. I've never thought of this. Yeah, we don't really consider magnetic field in supernova explosion. Maybe I don't know. We can
Yeah, I think the magnetic field, if you put a magnetic field in the model, that will change the stellar evolution because magnetic torque and especially the star rotate, then will change the evolution quite a lot, and that will change the white dwarf property, and that will affect the explosion. That's usually this way. And what? Next question, Wolfgang.
Okay, so you talked about the velocities measures near the peak. So I'm just curious, is there some monitoring of how the velocity changes function of time, and is that possible to tell about the mechanisms? Maybe those extra informations that could tell us there's two types of stuff or something like that. Is there this kind of situation?
Yes, there are some studies studying the gradient of the velocity, and they found you can also separate the supernova into high velocity gradient and low velocity gradients, type 1 supernova. But it's the same thing here because they found those high velocity gradient, those declines faster. It has high velocity gradient. They usually are high velocity supernova. If you have higher velocity, no matter for example, if you have higher velocity at peak, that means you also have higher velocity gradient compared to other normal velocity supernova. So the gradient and the velocity is related, tightly related.
Yeah, so let's tell us anything about the mechanism or from the theoretical point of view.
Yeah, so I don't think there's such as like using that's what one of my to-do lists, like using a gradient to probe, because it's not easy. If you need to have multiple epochs of spectroscopy observations. Usually, for these kind of studies, we usually have one epoch near the peak. So in the future, it would be best if you have very, high density spectroscopy observations. That's my hope. Which might reveal some additional, like you said, dimensions and interesting things.
Maybe I want to comment on this velocity question mentioned by Dingwen and maybe also related to Wolfgang. Is yes, the velocity of the ejecta change, but not much. That's because when the supernova explosion at the face, they shine to the lighter peak, and the ejecta enter so-called homologous expansion. So that means the ejecta is like frozenly expanded, and that velocity. Why you can do that? Because most of the explosion energy originally is internal energy. and then convert into the kinetic energy of the ejecta. So that will be travel, so like mostly frozen. So like also called a free expansion. So like the velocity you can think about almost like a constant. And then they can indicate the positions of the ejecta. So you do the radius and the velocity of the profile, you will see like this profile. So at that time we use velocity to indicate instead of the radius to the
So
position.
yeah, I think what Ken means that there's a velocity gradient, but it's usually dramatic at early times only. Maybe before the peak, there is a dramatic gradient. But after that, it's mostly linear or just very mild evolution.
So for example, the Yen-Chen say, oh, if the high velocity above the 12,000 kilometer per second, then at peak. But you at 100 days, a year later, almost the same. So the velocity won't not change very much in this case.
For a fast scalar wind, usually the scalar wind velocity is closely associated with the escape velocity. So this velocity seems to be much faster than the escape velocity, right?
Oh yeah. Yes.
The escape velocity will be maybe a few thousand. This is 12,000. It's much higher than that.
Yeah. It's an explosion, yeah.
It's on the surface. Yeah.
Yeah. It's not the Laura mentioned this hard wind or cold wind or maybe Boston or flavor is actually steady wind or erratic wind, but that's all the hard wind can go like a few thousand kilometers per second, 2 or 3. But the cold wind, so cold wind is like tens of the kilometers.
As I call it, sometimes the wind velocity will be 3 times the escape velocity.
Yeah.
So I didn't calculate this, but
So it's not, so this is related to the kinetic energy, which, the total energy by thermodynamic burning is about 10 to 51 Earth. And the binding energy of Waldorf is near 10 to the second mass, about 10 to the 50.
Yeah.
This additional energy, if you convert it to kinetic energy, it's something like this scale, 10,000.
Yeah, this is how we determine the explosion energy of the supernova. We measure how fast they move the ejecta, and we calculate the kinetic energy. And reverse, this energy was where are they from? They're from the explosion. So that's explosion energy. That's how we calculate.
so we have these different R. So the large R correspond to large dust grain, right?
What R?
The R, the
RB.
AB over EB minus
Oh,
B.
RB, okay.
Right, so large R means AB and AB are very similar. So small AB, right? It's B minus B, right? EB minus B is equal to AB minus AB. Okay,
Yes.
right?
Yes.
So large R means small AB,
Large R means.
which means larger dust grain.
Large dust,
You're correct. Large, you told me large R means large dust grain, small R means small dust grain.
Yes, that's the larger RB means larger grain size. So
Yeah.
that's interesting because they found for supernovae which show some circumstellar material, those signatures, they tend to have low RB. Because CSM, they tend to have low RB. Because those dust, they have been shocked by the supernova explosion. So that might change the dust grain size. So
Yeah.
I think that affected by
The CSM.
Yes. But just for some studies, they found this CSM scenario.
But the single degenerate, double degenerate, I know you don't care, but they do differ in the CSM.
Yes.
So this will affect this, right? Your
Uh,
supernova ejecta, interact with the CSM, and it will be absorbed by.
For double degenerate, it could also produce CSM. Yeah, just
Binary.
something.
You mean like a merger before? So it's a
Binary
kind of,
stuff.
so it's shredded each other.
Yeah, because they found it could produce something similar. The second wire was being tightly disrupted. And also some surrounding CSM is similar to.
So what's the signature for that kind of CSM?
What is the signature?
Signature, yeah.
I don't really know.
It's
I mean,
complicated.
because for CSM, the prediction is there could be some time varying sodium,
Yeah, so if it's a double degenerate, so before, when they're doing the tidal interaction and shred the surface, and that's almost toward the end of the merger, right? So before your gravitational wave sends off those beepers, whatever sound. So that CSM will not be extended like what we see in the single degenerate.
Yeah, no, it's probably correct. But that CSM, but it will be sufficient enough to affect the supernova light curve interaction.
Yes, you'll affect that, but
Yeah.
in a different way from the other kind.
Yes, yes.
You want to
Because,
call it CSM, don't confuse us. Let's just call it something else.
Common number.
Yeah, just they found this kind of.
Is it the merger at the end, is it common envelope? Do you call it common envelope?
Yeah, because it's sort of like two stars interacting in the entangled way and share some of the mass due to want to get rid of angular momentum.
Double degenerate.
Just like a Paul-Ricoeur's work. Which is this?
If asymmetric, there should be a kick velocity. Do you see any difference in the distribution of the kick velocity?
Kick.
Kick velocity of the neutron star.
You mean, yeah, I mean, there are some studies trying to, there's this kind of double detonation sub-Chandra model. It should produce high velocity. White
Of the ejecta.
Sorry?
Of the neutron star?
No, white dwarf.
No.
You're talking
after the explosion.
after the explosion, you mean
Yes,
neutron star?
kick.
Why?
Well, if the explosion is asymmetric, the newly formed neutron star should kick due to momentum conservation.
So what is
Actually, this case, 1A doesn't have a neutron star in the explosion. It's mostly the thermonuclear explosion. Unlike from the massive star called supernova.
So there is
But for single degenerate, then the normal star companion does get a kick. It does.
Single degenerate.
Single degenerate.
what?
Oh, normal.
The-
Oh,
the
companion
the
star.
companion, yeah, the companion.
Oh,
does
companion
that.
star.
Yeah, companion star could suffer some kick, but there's no neutron star over here.
Yeah, you are.
Yeah,
That's what you are looking for. Something for
yeah, the companion, the normal.
companion.
So
Surviving
the type
companion.
1A is either two white dwarfs or one white dwarf and one normal star.
So
So
actually,
two
like
white dwarfs
exposure
and
is
both
not
stars.
by neutron star. It's by like a nuclear bomb, thermonuclear runaway explosion, and it exploded entire white dwarf star.
I see, okay.
So, the kick is usually in top right, have the neutron star formation.
Okay.
You mentioned in the sub-theoretical model, the observing dioxide is important in affect the result. So is it possible that some high velocity ones are hidden in the normal velocity samples, and is it possible to distinguish them?
You mean the high velocity ones are hidden in normal velocity? Oh, you mean, what do you mean?
Because we did not
In terms of
observe
velocity,
the high velocity because of the dioxide.
Yeah, so that's why. So, for example, if this red curve is produced by sub-Chandra, then there should be some normal ones here, which is because of the different line of sight. If you're looking at supernovae at different locations, no, not in your line of sight, but from different unit angle, you can produce normal velocity supernovae, but still they share the same origin. They could all produced by sub-Chandra. So I don't know if that's.
So we cannot distinguish if they are sub-Chandra, but not in the current dioxide or the Chandra color mass model.
So it's hard. We can only now know that for those high velocity ones, it's probably more pure sample of sub-Chandra. But if it's normal velocity, it's hard to tell. That's what we are trying to study, to see maybe if you have a large sample of high velocity trying to study variety of parameters, you see if there are any normal velocity supernovae, they have the similar properties. They could have the same origin. But yes, it's hard to distinguish just if you only have velocity information.
Thank you.
I have one
Okay,
request to Ken.